Hi everyone, welcome to another session of the AFMC seminar series. Thanks for joining us. Today, actually, I'm hosting the Professor Martin Obligado from the Centrale Lille Institute, and he will deliver his actually latest research on the dissipation and intermittency in turbulent wakes. Very briefly regarding the Martin, I can mention that he is an expert in the experimental characterization and theoretical modeling of the single and the two-phase non-canonical turbulent flows, and his current research interests include the study of the gravitational settling of particles in turbulence, their clustering, and the hydrodynamics of the bubble column reactors. Thank you so much, Martin, for accepting our invitation, and we are all ears, and the floor is yours.
So thanks a lot, Javad, for the invitation and for the presentation, also to all the AFMS. So I am Martin Obligado. I will present about dissipation and intermittency in turbulent wakes, sometimes going to more general flows like grid turbulence. And this is a work that goes through several experiments made across the years. That's why there are so many colleagues as co-authors like Christos Basilikos and Mohammad Ahmad from my lab in LMFL in Lille. Also, there's Ingrid Neunaber that now she's an assistant professor in KTH Sweden. It has been, I think, 2 months ago, so I didn't update her status, but well, at the time she was with Amelie Ferran in Norway. And then there's some colleagues from Oldenburg University and Felix Schmidt, Andre Fuchs, and Joachim Painke, and finally John Farnsworth from University of Colorado Boulder, of Colorado. And I will present results from all these institutions and different experiments across this talk. Okay. So this is going to be about turbulent wakes and turbulent flows. I will try to express how do I understand turbulent flows and this is about experiments, but which is the theoretical framework that I will use to interpret and to study turbulent flows in wind tunnels using axisymmetric and different wakes. So as you know, well, all of you know that turbulence is present in a lot of systems at a lot of different scales. They can be natural systems like volcano eruptions, or you can see down on your right an axisymmetric turbulent wake, a DNS, a wind farm, and even astrophysical systems, which is all these very large set of systems and are turbulent, and they have a fundamental interest because they are very out of equilibrium systems that have many degrees of freedom, and it's a multi-scale phenomenon. So it's a phenomenon that is very hard to model, and in particular I will try to say which sense I will model the energy cascade in turbulence is this very well-known Richardson-Kolmogorov cascade, in which large vortices starts breaking up in smaller structures until dissipation and so on. So which is the mathematical background that I will use to model, or at least to understand this cascade. It will be through the Karman-Howard equation. In this case, the expression that you see there is for decaying homogeneous isotropic turbulence. I will also explain it in the sense of the Kolmogorov 1941 formalism. So the Karman-Howard equation is a transport equation for structure functions. You can see the definition of a structure function over here. It's just the average of the velocity differences at 2 points of space with an exponent n. And I will use other quantities across this talk that I will define a bit later, and I will get back to these quantities over here a bit later, just to say that the Karman-Howard equation is derived from the Navier-Stokes equations. It's an exact equation, and that has 58 terms. I forgot the exact number, but if we impose the flow to be homogeneous and isotropic, we can get this equation over here that it's simplified, and it's a transport equation between the second order and the third order structure functions, and this is an exact solution, I say this again, for homogeneous isotropic decaying turbulence. So how we can interpret the Kolmogorov phenomenology for this equation that we have over here? If the Reynolds number is large enough, we have enough separation of scales to say that there will be a range of scales R in which they are large enough that this term over here, the viscous term of the Karman-Howard equation, is negligible. I don't know if you can see my cursor, or otherwise just to say it's the second term on your left-hand side. The third term is the unsteady term, that it's also active for statistically steady flows. It's only active at large scales. So if we have enough separation of scales, there will be a range of scales in which the second and the third term can be neglected, and we will end up only with the first term on the left-hand side and the only term on the right-hand side. The term on your left, on your second equation, is the interscale energy flux, and the other term is dissipation. And this is what I will refer, and other people refer to as equilibrium. It's not equilibrium in a thermodynamical sense, it's just we say that in the K41 formalism, there's an equilibrium between interscale energy transfer and dissipation. So when I will later talk about non-equilibrium, is in the sense that this equality is no longer valid. Well, this is the well-known 4/5 law of turbulence, that if we integrate over a sphere with a radius more or less in the order of the integral scale, we can actually go from this equation over here to the so-called zeroth law of turbulence, in which dissipation goes like the RMS of the fluctuating velocity with an exponent 3 divided by L, which in this case is the integral length scale, times C epsilon, where C epsilon is a constant for a given set of boundary conditions. This implies that for a given generator, a given nozzle for a jet, a given grid, C epsilon is a constant, but it will change for different flows and different, let's say, grids and generators and so on. If we combine this equation with the definition of the Taylor scale lambda, which is defined with this 15 nu u prime square over epsilon, we can actually get an equation that it's mathematically expressed the same, but sometimes it's easier to measure, in which L over lambda goes like Reynolds lambda times this constant C epsilon. This is an equation with a strong physical meaning, because L over lambda is a ratio between a large scale and we could say a small scale, like lambda, so we can quantify the scale separation in a turbulent flow. And as we know, this ratio will increase for increasing Reynolds lambda. But it's also important because these two expressions not only have a physical meaning, they are also easy to measure, or easier to measure in a wind tunnel when compared to the full Kalman-Howard equation or other energy or momentum budgets. So this is what I will use. I will try to infer properties of the energy cascade from these two quantities over here that are, as I said, most of the time easier to measure. Of course, there's a very, very large amount of evidence that K41 scalings work pretty well. I choose on purpose two examples in which we see a transition between two regimes. You can see some results for fractal grids on your right, some results for an active grid, and from my group on your left is actually the active grid operated when it's completely open. So it's sort of a irregular, complex open grid. So we do see, for instance, on your right, that C epsilon tends to be a constant on this plot. The right side corresponds to and far away from the grid. The left area corresponds to near the grid. It's the inverse on the plot of L over lambda. And we see that the Kolmorov scalings do work, but there seems to be that in the near field of the grid, there's another turbulent state in which we have different laws, in which C epsilon is not a constant, and L over lambda doesn't go proportional to Reynolds lambda, but seems to be kind of a constant that depends, as you can see over here, on the free stream velocity of the fluid. While we could say that this is related to the near field of the flow, actually many flows seems to follow this in a controlled way. So there's some scaling laws that seems to actually model this area of the flow pretty well, in which in this new state of turbulence that we call non-equilibrium, but in the sense that I was saying before of this balance between dissipation and interscale energy transfer, there's this equality. If we don't have this equality, we'll refer to this cascade as non-equilibrium. That has been found, as I will show in a minute, in other flows. C epsilon is not a constant, but it's a ratio between two Reynolds numbers, one which is a Reynolds number that depends on the inlet properties of the fluid, and a second Reynolds number that depends on the local Reynolds number and local properties of the flow, like the integral scale and the RMS of the velocity. In this case, so C epsilon is no longer a constant, and L over lambda doesn't go like Reynolds lambda. It goes like the square root of the global Reynolds number. So for constant inlet conditions, we have the same ratio as we see if I come back in this plot over here, in which the plot is flat. So having a different energy cascade and a different closure for dissipation implies that we need to restate some theories and some ideas that we had before, including turbulent wakes, that will be the main topic of this talk over here. Just to say, there's also a lot of evidence. This has been found 10 years ago or so. And these non-equilibrium scalings have been found. I put some papers in which I participated, like interaction of wakes, an axisymmetric turbulent wake, but also in DNS and experiments, including prisms, slender bodies, and turbulent boundary layers, mixing layers, and several other flows. There seems to be a range in which we are out of Kolmogorov scalings, sorry, but we have this non-equilibrium cascade that has well-defined loss and scaling loss as well. So this takes me to the objective of my talks. First, I will show how we can include this non-canonical energy cascade within the theory of turbulent axisymmetric wakes. I will test it on different black bodies and trying to go to a more applied and industrial flow, try to see if we can apply also this approach to win the turbine-generated wakes. And I will also, so first discuss these three objectives that we will have over here, and I will try to take a few minutes to try to go beyond these ideas of scaling loss in wakes and discuss a bit about how we can add intermittency to this problem. And if I have time, a bit what happens if the flow is unsteady. Unsteady in the sense that large scales of the flow are also unsteady, like we are forcing the inflow in a particular way. So sorry, I will just mention briefly how the turbulent axisymmetric wakes can be modeled with these cascade ideas. First to say, there's still an ongoing debate, and some of you may not be aware that which are the scaling laws that control an axisymmetric wake is still up to debate. Is because these systems are very hard to simulate and very hard to measure in a wind tunnel, because we may have a small velocity deficit. I mean, when we try to measure this in the wind tunnel, very soon the velocity deficits are very small and they are masked by the turbulence intensity of the tunnel, so the natural fluctuations of the tunnel. We can reach the walls or the domain of our simulation very fast. So it's hard to find reliable result that can expand for further downstream enough to have a conclusive scalings about this loss. Actually, this phrase, I took it from a paper by Bill George. I forgot which one, but it's still an ongoing debate about this. And I will also show how this non-equilibrium cascade can be included to this debate and contribute to understand how to find scalings and so on. So I will always use the same quantities. U infinity is the free stream velocity of the flow. We will have a plate. As the plate is not always regular, it can have some fractal periphery, or else I will define the characteristic length of the plate with the square root of the frontal area. Then we have a wake width delta and a velocity deficit U0. Sorry, a centerline velocity deficit. Delta is defined in the standard way as a weighted average of the velocity deficit in the radial distance. The radial distance is r, the streamwise distance is x, and we can also define a momentum thickness that is related to the drag coefficient of the plate, and these two quantities are connected via momentum conservation. So this is a very old problem, even from Prandtl and before, but the most modern approach to obtain scaling loss for the axisymmetric wake has been actually proposed by Townsend and restated by George. So we will use the Run's equation of the flow. This is the traditional way, assuming that we have an axisymmetric and self-preserving flow. Then the standard way, or the old way, was to actually add an eddy viscosity assumption and get some scalings. But what Townsend and George propose is to use the kinetic energy balance, so we don't have to add any extra assumptions or eddy viscosity assumptions to the system. So I won't spend a lot of time on the math, just to show that it's actually an easy calculation to get to this. We have the Run's equation to the for the streamwise direction of an axisymmetric wake. R corresponds to the Reynolds stress. I had already defined the other terms. I will impose self-similar solutions to all the quantities. And we say self-preserving because it's a subtlety that we can have self-similarity of all quantities using the same normalization that will be delta. So we can define the self-similar variable using the delta. And like this, we can deduce these two equations over here. The problem is that we have three unknowns, delta, U0, and R0, and two equations. So the problem is not closed. And this is where either we have this eddy viscosity assumption, or we use the turbulent kinetic energy equation to try to close these equations. So if we go to the kinetic energy balance, we will once again impose self-similar solutions to all the terms in this equation. Well, I'm actually proposing a self-similar solution for production and transfer together, but that's another discussion. Wouldn't change the conclusions if I do it separately. So we have a kinetic energy, we have the product of production and transfer, and we have the dissipation that we call D, the self-similar quantity of dissipation. In this case, it may seem that we are in a worse situation because now we have the equations from before and these new equations, but it's 4 equations for 6 unknowns. But in this case, we have enough unknowns to start proposing physically based relations between them. For instance, as you see, we have D0. We can propose the C epsilon closure that is usually proposed in turbulence. So there's actually 3 assumptions that we have to add over here. One that is always implicit, that is the integral scale of turbulence and the wake width are proportional, because we are always assuming that delta can be used as representative of the larger scales of the flow. And as I said, an assumption of our dissipation, and then something that relates the centerline velocity deficit and the centerline kinetic energy. So this set of assumptions that the integral scale and delta are proportional, it has been verified in jets and wakes. We see that after 15 to 20 diameters, L over delta reaches a plateau. And the other assumptions, there's still some debate on this. We can see on a paper over here by Johansson and Bill George that they have some evidence that U0 squared goes like K0. We found some contradictive evidence of this. I won't spend many minutes on this, but there's an alternative that is a principle of constant anisotropy, that it's on some works we did that could replace or not this assumption, but at the end, for the final results, using one or the other, we will get the same final scaling laws. What is important is that at the end, we still need to propose a closure for dissipation, and it is here where Townsend and George propose to use that dissipation, or D0 goes like C epsilon U prime cube over L. And at the time where we did this formulation and these experiments, we're expecting that a square plate, like the one that you can see over here, was going to follow this kind of laws, because there was some previous evidence on this. We may see later that it's not exactly the case. And we're expecting from some previous works that in Christos Basilikos' group, that a fractal plate like this was going to be following non-equilibrium scaling, so C epsilon was not going to be a constant. So what is very interesting about the problem of turbulent wakes is like we can actually close the equations proposing either equilibrium or either non-equilibrium, and we can get mathematically consistent scaling laws for one case or the other. So of course, if we propose equilibrium, we get the standard and very well-known scaling laws with a minus 2/3 and a 1/3 for the velocity deficit and the wake width respectively. But we get very similar scaling laws for the non-equilibrium cascade, but the exponents, well, the prefactors are a bit different, but more importantly, the exponents are also slightly different. We get a minus 2/3 for the velocity deficit and a -1 in the case of non-equilibrium. And also we have the 1/3 for equilibrium and a 1.5 for non-equilibrium. So before going to the experimental results, this is a very nice example of the multi-scale nature of turbulence, because if we change a small scale feature like the dissipation scaling, we can see how a large scale average quantity like U0 and delta can be modified in its actual scaling laws and actual properties. Okay, so trying to test this, as I said, we tried to use a regular plate with, at the time we thought it was going to have a K41 scalings, and we call this a fractal or irregular plate. We did this on a wind tunnel. We had a Reynolds lambda of 40,000. And what we did, assuming axisymmetry, we did vertical profiles with a hot wire, trying to have the average shape of the wake for different streamwise distances, ranging from 5 diameters or square root of the areas up to 50. And we made sure that we were able to resolve dissipation. So we did at least 1 minute of measurement at each different point that we did. So, well, to be sure that we were within this Townsend-George background, we checked that the flow was axisymmetric. I'm not showing it here. We checked that the flow, at least what we can see with a hot wire, it's self-preserving or self-similar. And then we went to the scaling laws. So what we found is that the problem, as if we go back to the scaling laws, we have this expression that it's x minus x0 times an exponent. So we are fitting the prefactor, the exponent, and the virtual origin. So either, for instance, for the square, if we try equilibrium or non-equilibrium, both fits are very good. And what is worse, we cannot actually disentangle only by fitting which family of scaling laws is the best. So actually, to understand what's happening with the turbulence cascade and be able to extrapolate to longer distances, to longer streamwise distances, we need to access C epsilon. And this is what we did, and this is when we got a surprise, because, well, we complemented this with a DNS that I'm not showing here, but we found that the non-equilibrium scaling laws, I'm normalizing with the momentum thickness theta. If we normalize with the non-equilibrium, for the fractals, as we expected, it becomes flat, and for non-equilibrium, it's never flat, so the fractal plate seems to follow non-equilibrium scalings. But in this reduced range from 5 to 50 diameters, the K41 scalings never perform well. So C epsilon actually evolves according non-equilibrium scalings. So again, for this range from 5 to 50, seems that both plates follow non-equilibrium scalings. So just to make some partial summary, it's nice to see how the Townsend-George theory can be adapted to well, particularly this non-equilibrium, but some non-canonical energy cascades. As I just shown, to actually know which kind of scalings we have is hard just by doing fits, and I will continue discussing this in the next slide. But we actually need to access more information about the cascade, like quantifying C epsilon. And then it seems that a very large set of plates follow non-equilibrium cascades, and at least the regular and irregular plates that we tested over here. So this motivated us to say, okay, what happens if we have more realistic flows? What happens if we have scaled wind turbines? So something I didn't say, the previous experiments were performed during actually my postdoc some time ago in Basilikos group in Imperial College London. And if we wanted to test a scaled wind turbine, we needed a bigger tunnel, both in the sense of the streamwise extension and the cross-section of it. So this has been performed later at Oldenburg University, where they have this amazing wind tunnel that has a 3x3 cross-section in the test section, and it's 30 meters long. And on top of this, we can add different grids that can be passive or active. In this case, we used passive grids to try to have some turbulence. And there's also available scale turbines that we can control the pitch, and we can operate them in an optimal TSR, and we can also play with the TSR. So we use this wind turbine. In this case, instead, before we're moving the hot wire, assuming axisymmetry, here we had actually 24 hot wires at the same time synchronized. So this actually makes the measurements faster. We can do a test at one position, then we move this chariot that you can see over here, and like this, still assuming axisymmetry, we can get the full evolution of the turbine. What we did, we used the laminar. When I say laminar inflow, it's a wind tunnel with nothing, so just very, very low turbulence intensity. And the turbulent inflow was a passive grid that gives a 2%-ish turbulence rate, so it's not really a realistic atmospheric turbulence scenario, but it's okay. And like this, we were able to go 33 diameters downstream. As you see, the Mojito, this turbine is 58 centimeters, so it implies that we've been almost 20-ish meters downstream the generator. So trying to have many different cases, once more, we wanted to see, can we see some effects or some traces of the non-equilibrium cascade or the K41 in this turbine? So we tried two different Reynolds numbers, so two different inflow velocities, different tip speed ratios, but by changing the blade pitch angle. And so we have, I will come back to the previous slide, we have all these hot wires, but only the one at the center has enough temporal resolution to resolve dissipation and all the relevant turbulence quantities. So basically for a given inflow, we have three different cases, two with the optimal diameter Reynolds number, one that it's underperforming in terms of Reynolds number, and one which has the optimal pitch angle, so the optimal TSR, and the other that is off because we changed this pitch angle. First, just to show the raw data that we have and the kind of results that we can see. We had already seen in a previous experiment, also working with Neunaber and Painke in Oldenburg, that self-similarity and axisymmetry are already achieved at 6 diameters. And we see that before going to the cascade, both the wake width and the velocity deficit seems to be affected by the working condition. In particular, the wake width seems to be strongly dependent. When we have this different TSR in our flow, we see that the wake width is very different compared to the other cases that we studied. We also checked how does the turbulence properties of the flow look on these three different cases. Remember, so case 2 is the one that has the optimal Reynolds number, but the wrong TSR, and case 3 has a lower Reynolds number, and we see that the optimal case in which the turbine is operating, it was manufactured to work optimally in the conditions of the case 1. We have a stronger turbulent flow and a larger integral scale, and this was just the beginning to start thinking about, okay, can we first see if the wind turbine follows? Are we in the far wake enough to see that these power law scalings from Townsend and George apply to our flow? We saw that it is the case. Now I'm showing results for both the laminar and the experiments, and the solid lines are the fits that work pretty well. How we did these fits in this case is delta and the velocity deficit were fit simultaneously in a way that the virtual origin is the same in both cases, because the equations imply that they should be the same. And here we found a first issue is that when we apply these fits to our data, and alpha and beta seems to be a bit all over the place. We can see that sometimes we are closer to equilibrium, sometimes we are closer to non-equilibrium, and the problem may be related that to actually fit all these quantities, we should have a much larger streamwise range. So we are a bit limited here. Maybe it's a bit the same what happened with the bluff bodies. So once more, to actually see what's going on here, we need to go to C epsilon and see which kind of cascade or with which cascade we are consistent in our measurements. Each color that you see here corresponds to a different realization, so a given inflow and a given case, 1, 2, or 3, and all the streamwise conditions together. And then you can see this cross and star markers that corresponds to the rotor fixed and the grid alone. So C epsilon is constructed with the cube of the RMS of the velocity, the dissipation, and integral scale. So it has altogether a 15% of uncertainty. The error is in the order of 15%. So what we see is that actually C epsilon is constant for each realization. And we may have some small dependency, but we know this C epsilon can be constant for a given set of boundary conditions that implies different operation regimes of the wind turbine. And it is what we see over here. So it seems to be that the wind turbine, in the same range where we saw non-equilibrium for the bluff bodies, we see K41 scalings for the wind turbine. My guess is that the rotation of the turbine breaks turbulence structures so well and so efficiently that we reach the very far wake regime much faster than for a bluff body. requires more time to develop. Still, we should have more studies to actually to explore a broader range of Reynolds numbers, maybe reaching higher velocities, not possible on this tunnel, to try to understand if there is or not a trend with the Reynolds number and the operating conditions. Just to make a little comment on because there's a lot of wake models trying to describe these wakes, I just focus on these power laws that are the far wake theory developed by Townsend and George. But there's also many, many models. I will just mention two that are very popular, the Jensen model and the Bastanka and Porter model. So we got an idea because we had this problem that fitting virtual origins and exponents was making our fits always perform very well. We said, okay, what happens if we add as an ad hoc assumption a virtual origin to all these models that we have over here? What is the physical sense of this? In the Townsend-George theory, the virtual origin quantifies like the production. It's like a leading order, a leading parameter to quantify the production zone of the wake and correct our scalings with this virtual origin. We can add this as an ad hoc assumption to all the other models. And what we saw is that when we add this virtual origin, let me just say this one moment again. When, for instance, you can see the Jensen model here, we have times x. What happens if we replace x by x minus x0, and we also fit this x0 parameter? But came as a surprise that all these models have different, I also added the Aitken model. They all perform in different ways. Sometimes they perform well, sometimes they perform not very well. But when we add this virtual origin, all models fit very, very well our data. So it seems to be a length scale that models the production range. As all models have some physics on them, they can be based on momentum conservation, mass conservation, the Brand's equations. They all capture some physics of the wake, and by adding a virtual origin, we managed to make them perform. And we even added some some LiDAR data and some field measurements. And once more, we see that even field measurements that are very noisy and no model seems to fit them well in a large range, they work well. With this case, as you can see also in this slide, this is always field measurements. Once we add a virtual origin, okay, it's not as good as for the wind tunnel data, but we see that LiDAR measurements still make all the models fit well field data. Okay, so this is the end of part one. I think I hope in the next 10 minutes to cover the other two parts. So the Townsend-George theory can be adapted to adapt this cascade, as we saw. But what we saw working with the wind turbine is that the streamwise evolution is strongly dependent on the operating conditions, but adding a virtual origin seems to make all models perform pretty well to model wind tunnel turbines with different inflows and field measurements as well. But more study, we would like to have some scaling laws to understand how this virtual origin behaves in all these cases. But okay, I have been discussing scaling laws. So of course, velocity deficit and wake width may be the two most interesting quantities when we want to model a wind farm or to understand what's a wake doing. Can we go a bit beyond and try to add what happens with small scale intermittency in the wakes and with these different cascades that we can have over here? And I will just mention, as we already discussed in the first part, the energy cascade is a mechanism to dissipate at large Reynolds numbers, and we saw the Richardson-Kolmogorov. It's like the sketch that helps us to understand how the energy cascade evolves across scales. Intermittency can be seen in this image that I took from a paper of Fritsch. If we high-pass filter a signal, we see that turbulence also appears as bursts of energy in the signal. So these small-scale dynamics can appear like in bursts that are present both in the inertial and in the dissipative ranges. And well, if you have studied turbulence, you know that this is related to a lot of but this makes K41 to not work anymore. There's the K62 theory, the multifractal model. There's a lot of models to try to understand intermittency. It's not fully explained, even there's a lot of progress on it. Here, I will try first to show how we can quantify intermittency, and both quantities are hard to characterize experimentally. I already showed how we can bypass some difficulties with C epsilon, and there's no a clear relation between both phenomena. No, there's no a clear connection between both cases, and I think we may have found a good relation to work with intermittency and the energy cascade. So how can we quantify intermittency? Intermittency is then therefore related to extreme events in the velocity increments. So if we take the velocity increments, they are Gaussian for large increments, but when we start doing delta U for small values of R, the PDF of delta U is no longer Gaussian and starts having tails because we have extreme events. Therefore, a way to characterize intermittency, there are many, but the one I will use here is to characterize intermittency through these deviations of Gaussianity, for instance, using the flatness of the distribution. So we have the velocity increments, and we'll define the flatness of these increments for a given scale R. So we expect to have a 3 for large values of R and values that go up for small values of R. So a way of doing this is f is the flatness. We'll define the shape parameter, defined as L squared goes like the logarithm of f over 3 in a way that we get a 0 and for the Gaussian case. And like this, there's been some work so that in the inertial range of turbulence, and we have a self-similar behavior of some quantities, we can see that this lambda squared parameter, that it's 0 when we have no intermittency and bigger than 0 when we have intermittency at the scale R, will follow this law over here, that we have this lambda 0 and this value of mu, that is the quantity associated to the inertial range of this intermittent behavior. So we can actually quantify intermittency with mu, that is a scalar quantity. So this very complicated phenomenon that requires 2-point quantities to be evaluated, we could quantify it with the value of mu, that is kind of the intensity or the slope of this shape parameter in the inertial range. Just to say, it's not going to be part of this talk, but there's been a lot of theory by Castin, Penke, and collaborators in which we can relate this value of mu with the aberrations of the structure functions in the K62 framework, with this kind of corrections to the Kolmogorov exponent that you may be related with. And this is a bit the point that we used that inspired this work over here. Part 1 was a bit related with the graph that you can see on your left. It was assumed that C epsilon was a constant. Now we know that in some flows, in some ranges, C epsilon may be a constant in some ranges, but not a constant in some other ranges following this non-equilibrium laws. But also, this quantity mu is expected to be a constant for large values of Reynolds number. So this is expressed as the 6th order normalized structure function, but in this case flat for different flows. This is a compilation of results, implies that this mu tends to be a constant. This is equivalent of a mu value of 0.2 across many different flows. As I already shown for the dissipation, some works are at odds with this evidence. Other works also suggest that mu is not constant. We want to see, can we actually start playing with these two constants and trying to find relations between them to see if this lack of universality at least is recovered in a sort of relation between mu and C epsilon. For this, we did another set of experiments, this time in Légy wind tunnel in Grenoble. We did, you can see here a photo with 4 different plates, 4 different cylinders, so we have axisymmetric and planar wakes. We had 3 different inflows, laminar inflow, passive grid inflow, and active grid inflow, and also for different velocities. The point here was to gather a lot of information about mu and C epsilon to be able to explore a very, very large portion of the parameter space and different regimes. And that's how Felix Schmidt, the PhD student, gathered 5,000-ish data points in which we, for this presentation over here, we just have the 400 center line time signals for all these conditions. And for all these conditions, we quantified both mu and C epsilon. C epsilon well, both with single hot wires that actually have enough temporal resolution to get all these quantities. And so having these two values and being sure in the very near wake we may not resolve all the turbulence scales. In the very far wake, the separation of scales may not be very good. I don't want to lose a lot of time on this. We had a lot of criteria in terms of Gaussianity of some increments, the spectra of velocity, and at the end, well, we had this selection criteria trying to have only data that fulfills these requirements to be consistent and develop turbulence, and we ended up with 300 points for these 21 cases, and we also added some literature data for grids and jets. And if you see all together, we can see that C epsilon, as we know, for this range of the wakes, is not constant for all our cases. You can see C corresponds to cylinders, D to disks, and G to different grids. C epsilon is not constant, and also, which is interesting, is mu is not constant, and also has different trends. There seems to be some relations with Reynolds lambda, but what we found is that if we plot mu, so this parameter related to intermittency versus C epsilon, we see a very clear trend that emerges between these two quantities. Actually, mu times C epsilon is a constant, okay, almost a constant, but mu times C epsilon can be modeled as a constant, as we can see over here. Alpha is mu times C epsilon, that is a value of 0.10, and we see that all our data fits this data, and other data that we have been added later seems to follow this law that mu times C epsilon is a constant. And to our best knowledge, this is the first time a so clear relation between these two quantities is found experimentally. There was always the question, as we had these trends with Reynolds lambda, is this dependent on Reynolds lambda? And we saw, no, this is, the color represents the value of the Reynolds lambda, and we see that there's no trend with Reynolds lambda. This law works, and not because there's a trend with Reynolds, it's not a Reynolds lambda dependent law, it's just an inner trend that seems to be present in our measurements and in measurements from different tunnels and different groups, etc. So I think I'm a bit out of time, but this is only 2 minutes, so I hope Java just tell me to stop if it's too much, but I think I can present this in a couple of minutes. I just wanted to, so we actually saw what happens if we have a constant inflow, how we can relate dissipation and intermittency. The next step that we wanted to see is what happens if the flow is unsteady. Of course, the turbulence is always unsteady, but it's the large scales are statistically steady. What happens if the inflow is actually modulated following a sinusoidal inflow velocity? This case was John Farnsworth that did experiments at Boulder Wind Tunnel, where he has a very nice, he can put grids, but also there's some sort of active grid, I know how to say, that can open and close very fast. So we can actually modulate the flow with frequencies up to 1 Hertz and actually try these different grids. So he did some PIV, but here I will show only hot wire results. And what we have is results like this. The velocity for the different grids is actually modulated following this sinusoidal form. We used the hot wire, so to actually be able to quantify Reynolds lambda, C epsilon, mu, etc. with a single hot wire, it's not so easy. We do some windowing with a window size large enough that allow us to have locally these quantities across the path of this velocity. We are currently verifying this with DNS, and the results I will show right now are confirmed by the DNS, but I won't show them over here because they are not mature enough, maybe. But so this local averaging has also been used by another group that has been working with unsteady turbulence and a hot wire. But so you can see that Reynolds lambda, C epsilon, and the velocity vary over time with this windowing scheme. And what we found is that C epsilon versus Reynolds lambda do follow this law, that this non-equilibrium law, in which non-equilibrium law can be demonstrated that C epsilon should go like Reynolds lambda -1. This exponent -1 is not clear, but when Reynolds lambda increases, C epsilon should decrease, and this is what we see here. But we also see that when the velocity increases, C epsilon follows a curve, and when the velocity decreases, it follows another curve. And there's a very big and clear hysteresis cycle in this relation. So this is very interesting because it means that turbulence dissipate differently when we increase the velocity and we decrease the velocity. So we tried many different incoming velocities, many different grids, many different distances. We always see this hysteresis cycle. And this takes me back to the beginning of the talk. Remember that I said we will neglect the unsteady term of the flow because we have statistically steady turbulence. In this case, it's no longer the case. And we should be able to define an unsteady function. I will define it with this term over here. I can define an non-steady term in this way. And what we expect to see is that this unsteady term should be more or less controlling the intensity of this hysteresis that we see. So we can quantify the hysteresis area that we see in this cycle, and we call this area delta, and we see that delta goes like a Struhal number that we can define with the modulation of the tunnel times the amplitude. There's one outlier, but this works pretty well. And just to show that this is related to the Karman-Howard and this unsteady term, what we did is to quantify this unsteady term with a hot wire, and we see that the unsteady term is a function of R. But if we evaluate the unsteady term at the lambda, at the Taylor scale, it follows a very, very clear, but has a very clear linear trend with this Struhal times the amplitude number. So both this quantity delta and this non-steady term are proportional, and therefore we can actually start going a bit, this is very preliminary, but we can start going a bit beyond steady turbulence, and with these simple ideas and this simple way of assessing the cascade, access this quantity F and understand the unsteady flows. But this is a first step. So this is all for me. Thank you very much for following this.
Thank you so much, Martin, for delivering such an informative presentation of the dissipation and intermittency in the turbulent wave. So from the audience, if you have any question, please speak up or type in the chat box. Any question?
I ask one question? Well, thank you for the interesting talk. I was just thinking, reading your open questions here, the under-resolved data sets, like real atmospheric flow, for example, for wind turbine. And I was thinking of the correlation with the unsteady flow then, which would exist in real wind conditions. Just wanted to hear your thoughts about this.
Yeah, that's a good point that I didn't thought about maybe. So in wind energy, we have this idea that we will take 10-minute signal, no? Where the atmosphere is more or less steady. We could actually model this, and this unsteady term needs to be evaluated at lambda. And this law that we found, it's when we evaluate it at lambda, and lambda in field conditions, many times we can resolve it. We cannot resolve the Kolmogorov scale to have a deep turbulence analysis, but we can get lambda or infer lambda and get this function over there. So I think it could be, we didn't try yet, but we could adapt this to, we don't need a very good resolution to actually assess this. But we haven't done it yet.
Interesting to see if the sort of relationships that you're seeing with the unsteady flow, and apply that to field data. Yeah, very interesting.
Yes. One issue there, will be to see if we can actually have at least some. So C epsilon does require to resolve the Kolmogorov scale, because we need to have the dissipation, but maybe we could infer at least some approximation of C epsilon to see if we have some hysteresis, and then we can use this F to quantify the unsteadiness. That could be done. It's a good idea.
I may ask another question about the virtual origin that you mentioned in the first part. If I recall correctly, you said that the virtual origin is also solved in the curve fitting. So it's actually varying for different cases. And that's
Yes.
how we're getting the fit between all models. How do you interpret the virtual origin physically?
Okay, maybe we can see it on this figure. Maybe, yeah, could have spent a bit of more of time here, because we see that the velocity deficit increases and then it decreases. Not turbulence. There's a production range of turbulence, and then everything decays. So the virtual origins quantifies this production, this production range of the turbulence. So at the end, we'll more or less adapt our scalings to which is the point in which the energy and the mean velocity are, well, the mean velocity deficit are decaying together. So it does quantify this area over here that you see from 0 to 7D, in which turbulence is still building up and we are not in an actual decaying wake.
Yeah, that makes sense. Thank you.
Thank you.
Any other question? So once again, thank you so much, Martin, for joining us and presenting actually your research, latest research, and appreciate that. Thank you.
Thanks a lot. Bye-bye.